In this video, I'm reviewing the 2025 independent trial that I set. So we start with the multiple choice first of all. Which of the following best explains the purpose of plasticizers as additives? And this is, of course, it increases moldability. You can see that on page 138 of the engineering book. Question 2, how is plastic deformation of a material shown on a stress-strain diagram? Plastic deformation always occurs after the limit of proportionality, which is a straight line section. So C is the answer there. Question 3, which best describes geostationary satellites? Of course, these are the ones that remain fixed relative to the Earth's surface. Question 4, what's the reason why some electrical appliances do not require an earth connection? And because they're double insulated, and you see that with the concentric square on the side of the appliance. Question 5, why is aircraft landing gear made by forging instead of sand casting? Landing gear has to be tough because it takes impact loading all the time. So D is the correct answer there. Improves toughness and durability. In fact, nothing on an aircraft is sand casted. Okay, question 6. Which best describes the most effective galvanizing process? By far the most effective is dipping in molten zinc because you get an intermolecular bond to the zinc layer. Question 7, an object is placed on an inclined plane with a friction coefficient of 0.4. What's the angle of repose? Of course, the angle of repose, the tangent of the angle is equal to the coefficient of friction and inverse tan, so you get 21.8 and 22 is the correct answer there. Question 8, the belt and pulley system shown operates at an efficiency of 88%. What's the mechanical advantage? So the first thing you do is to get the velocity ratio. And the velocity ratio, remember, is the inverse. It's the driven divided by the driver. And so you get a velocity ratio of 2.75. And remember, mechanical advantage varies with velocity ratio according to the efficiency of the machine. So mechanical advantage equals the efficiency times velocity ratio. Make sure that you don't multiply that by 88. It's 0.88 because you've got to convert it to a numerical value. And so the answer is 2.42, and which is A. Where does corrosion take place in metals? Corrosion always occurs at the anode, where you have a loss of electrons. Question 10. Why are alloys stronger than pure metals? There are three things that inhibit the movement of dislocations. One is foreign atoms, the other is grain boundaries, and the other one is other dislocations. So D is the correct answer there. The diagram shows two NAND gates connected in series. What single logic gate is equivalent to this circuit? So when you've got a 0 going in here, you just interpret that as two zeros for A and B. So you do your truth table here, and you can see that the logic gate that is shown by this is an AND, because you get a positive feed out when you have an input of 1 for A and B. Next question is on mild steel structures. Plain carbon steel microstructures shown below. Which steel cannot be toughened? You know that any steel that has below about 0.3% carbon cannot be heat treated. The only way that you can harden that is by work hardening, and so B is the correct answer there. Question 13, which of the following correctly describes a 10 kilowatt hour battery? It is C here because it can supply 1 kilowatt for 10 hours or 10 kilowatts in 1 hour. Question 14, which lattice structure forms when a medium to high carbon steel is quenched from red heat? Remember, that is always an intermediate phase between face centered cubic at red heat to body centered cubic at room temperature. And if you quench it, it hasn't got enough time to change from face centered cubic to body centered cubic. So it goes to the intermediate phase of body centered tetragonal, which is called Martensite, which is C. The tensile test piece fails at a load of 50 kilonewtons. The original diameter was 510. A necking reduced the diameter of fracture at the fracture at as by 6. What's the true stress at the failure? So this is how you should set it out. So you've got stress, which is true, over load over area of fracture. Now you've got to use this area, the area at fracture, not that area there. And so make sure that you put the numerical value in. You can't put kilonewtons in unless you know what you're doing. So the area of fracture is pi r squared, and you use the phi 6 and multiply it by 10 to the minus 6 to bring it to meters squared, and the answer comes out at 1768 megapascals. Question 16, which drawing correctly represents the sectioning of a stud in a single block of steel according to AS 1100? This one's wrong because the sectioning goes through the threaded stud. This one is wrong because it's the same metal both sides and yet you've got different hatching angles. This one is correct because you've got the area, the thread section, but you haven't sectioned the thread on the stud. This one's incorrect because it's sectioned in the stud, which you shouldn't do. Question 17, which electronic component in a circuit functions as both a switch and an amplifier? Make sure that you know this. It's a transistor, and the transistor's got 3 terminals, and it acts both as a switch and an amplifier. Which statement best describes dye penetrant crack testing? Dye penetrant, you should make sure that you remember that it's only used on surface cracks. It can't detect deep surface cracks. And so A is the correct answer there. Here you have 2 steel rivets joining 2 plates. You've got to work out what the appropriate diameter of the rivets is. If the shear strength of the rivet material is 300 megapascals, set it out the same as before. Shear stress equals load over area shear. The shear stress is 300 times 10 to the 6 pascals. Don't put megapascals in here. The load is 47 kilonewtons times 10 cube newtons. And the area of shear, because there's 2 rivets, it's 2 pi r squared multiplied by 10 to the minus 6. And then you transpose the equation and you'll get r is equal to 5. So therefore the diameter is 10 millimeters. And so the answer is A. Where should steel reinforcing be placed in a reinforced concrete slab? Always where the area is in tension of the slab, that's in tension. And so D is the correct answer there. Now, next question is a truss question. And first thing you've got to do is find the reactions. And so the left reaction here, make sure that the first thing you do with a roller is you draw in the reaction and then have a look at the force that's being applied, and you can see by logic that that will go vertically up. Make sure you tell the examiner that it's at 90 degrees and you've got 1 mark there because the last point in the marking scale will say something like, demonstrate some knowledge of the question. And then probably the best way of doing this is, if you're going to do it analytically, I'll show you how it's done graphically in a moment. You break this force up into components. And so this horizontal component will be 20 cos 60, which will be 10, and the vertical component will be 20 sine 60, which will be 17.32. Okay, so the first thing you do is you take moments about the right, the pin, and so that you can get the reaction at the roller. And don't forget, this is only diagrammatic. They never use rollers anymore because they require too much maintenance and they're not effective. They rust out. They normally use a slider, which is like this, and that will still have a reaction at 90 degrees. So let's have a look at this. So you've got RL times 9. You've got all the dimensions up here, plus 10 times 3. So don't forget this horizontal component. That will be 10 times the perpendicular distance, which will be 3, minus 17.32. So this one here, relative to that, is going anti-clockwise. So that's negative, and that equals 0. Now, when we get a positive answer here, it indicates that that direction or the sense is correct. Sometimes you might get a force going down at these reactions, but they'll still show the roller this way. So just use logic to see how it goes. Now, the only horizontal force is this one here. So straight away, you can draw that force there, and you can say that that is 10 kilonewtons. You don't have to do this. You don't have to do sum of the horizontal force equals that, right, and put that, do that. It'll save you time. You just put that there and you put 10 kilonewtons there, and the examiner will realize exactly what you've done there. Then the next one is you have to do this vertical force here, and that will be at 90 degrees. And then we resolve this using Pythagoras, and then we get the reaction at R, reaction right. And then we have to find theta, that angle, the acute angle of the horizontal. And so this is how it's been done. We say sum of the vertical forces equals 0. So we've got 8.2, which is this force here, minus 17.2, which is that force there, plus RRY, which is this force here, equals 0. So we've got 9.1. Use Pythagoras, and you'll get the resultant of those two forces at 13.5 kilonewtons. And then you work out the angle using tan, and you can get the angle of the horizontal. Now, the other way of doing it, and I think it's quite a bit easier, is to use graphical methods. So that if you can see that there's only 3 forces acting, there's one force there, one there, and one there, you can use the 3-force rule. The 3-force rule says if a body's in equilibrium and only 3 forces acting, the 3 forces will all be concurrent. So if you continue this force up here until it hits that force there, there's the point of concurrence, and this other force has to go through that point. So as soon as you've got that, you do a scale, work out a scale, and remember when you do a solution graphically, you get 10% leeway in the HSC. And so the next thing you do is use Bose notation. I use Bose notation all the time because it makes life easy. So around here, I've put X. I haven't used A and B because it's used down there. And then Y between there, and then Z between there. And then you start off with the known force. So you start here, and you know that's 20 kilonewtons, and that equals 100 millimeters. So you draw that 100 millimeters long, make sure it's accurate. And so that force is YZ. So you put little y, little z down there. Then you go read it clockwise, and the next force you come to is ZX. And ZX goes vertically up, and we don't know how far it goes, but we know that it will end at that other force there. And so this force here is ZX, and the last force is XY, and it's got to go through Y, and so it's just that force there. So there's your force triangle, and you just scale off this distance here to get the reaction at the right reaction, and you get the magnitude. You put your protractor on here, you get the direction there, and you can just scale off this distance here, and you'll get the reaction left size there. And so this is how it's all written. Okay, so that's how you do that graphically. Now, next one is traditionally a difficult question for most students, and that is finding the forces in members. So you're asked to find the force in members AB, AC, and CD. So when you have a look at it, AB has got no external forces on it. And so all these members here are redundant members as it's loaded here. So that's got no force in, that's got no force in, that's got no force in. But whenever you see a member joining a chord, that force there is zero in that. So 1, 2, 3, 4 of these are redundant members. So let's do AB. Force in AB equals zero by observation, or if you want to, when you find out the force in this member, you can take moments about there and you'll see that it will be redundant. So first thing you do is you put a section through the three members. Make sure you make it a chain line because that's a section. You tell the examiner that you're going to take the left or right hand side. We're going to take the left hand side. I always put guess at tension. So I'm going to say that's in tension. And I'm going to say that's in tension. So I'm going to ignore the right-hand side, but we can still take moments about any point on the right-hand side. When you've got horizontal top chord and a horizontal bottom chord, you can break this force up into components. And if you break it up into a vertical component, that will be AC sine 45 because that angle there is 45. So I've done this over here. I've said sum of the vertical forces equals zero. And so I've got 8.2, which is a reaction left going up, plus 0.707 AC, which is sine 45 AC equals zero. So therefore AC equals minus 11.6. And the negative tells you that that's going in the other direction. So therefore it's in compression. And we've mentioned the force in AB is zero by observation. Then to get the force in CD, we take moments about A. And so I say the sum of the moments about A equals zero, and clockwise is positive. So we've got DC, which is negative because I've said it's in tension, times 3, the perpendicular distance, plus 8.2 times 3, which is the left reaction, equals 0. So therefore, DC equals plus 8.2 kilonewtons. And because it's plus, it's in tension. And that's how you do those method of section questions. Now, the next question is, we've done that. The next question is C, 21C. The truss members are made from steel angle bar with a Young's modulus of 200 gigapascals and a cross-sectional area of 900 millimeters squared. For another loading situation, one truss member is 3 meters long, is subjected to a 15 kilonewton tensile force. Determine the extension of the truss member in millimeters when the 15 kilonewton force is acting. Now, the best way to do this is using the Ply formula. And the Ply formula is explained on page 34 of the workbook. So you write down your formula, you write down all of the values here, and then substitute. So we've got delta L is equal to P, the load is 15 times 10 cubed, times the length of the member, which is 3 meters, divided by the Young's modulus, which is 200 times 10 to the 9, 200 gigapascals, and divided by 900 square millimeters, convert that to meters, and you multiply it by 10 to the minus 6, of course. And so the answer will be in meters, and we want it generally in millimeters because it's asked down here, and so it's 0.25 millimeters. Now, the next question involves pitot tubes, and the pitot tube are these tubes you see at the front of the aircraft, and these are designed to give the plane its airspeed. And this is how it works. So you've got air, dynamic air, rushing in down here. You've got static air, which is air within the boundary layer of the pitot tube, and that's probably 2 or 3 atoms wide, and this gives the pressure at any altitude because it's vented into the boundary layer. And so the total pressure occurs down here. And we want the dynamic pressure so that it can be scaled to airspeed. And so down the bottom here is a pressure transducer. And a transducer is a silicon cell which it's got a piezoelectric effect so that when you apply a mechanical load to it, it gives a electrical signal out. And also they use it in smoke alarms. When you apply electric current to it, it gives out a mechanical movement. It moves. And so the idea to get the total pressure is equal to the static pressure plus the dynamic pressure. But we want the dynamic pressure because we want to see what the airspeed is going through there. So therefore, the dynamic pressure is the total pressure minus the static pressure. And that's what this pressure transducer shows down here. And that's how a pitot tube works. Question 22B, ultrasonic testing is a widely used non-destructive test method for inspecting aircraft components. Explain the purpose of ultrasonic testing and describe the process of how it's conducted. So you've got to know that ultrasonic testing will test deep floors, not only surface floors, but deep floors, but it's mainly used for deep floors in materials. And The idea is that you've got a transducer which sends the ultrasonic waves through the component, and if there is a defect or a void or a crack, it reflects those back, and these show up on a cathode ray oscilloscope, and it is calibrated to see what the depth of the floor is. And so it's explained here, um, uh, and that's worth 4 marks, which it's a fair number of marks for a question like that. So make sure that you learn all of these facts. Explain 2 key differences between turbofan and turbojet aircraft. Turbofan is the engine that's used on virtually all commercial aircraft. A turbojet is generally used for mainly fighter jets and supersonic aircraft. They're very noisy, and they're not allowed to be used in commercial aircraft anymore because of their noise. Now, the major difference is that you've got a heavy duty power turbine, which drives a fan at the front, and the fan produces around about 80% of the thrust through the nacelle, and whereas a turbojet has all of the air through the compressor, the combustion chambers, and the power turbine. And because you've got high wind shear, you've got to have the same momentum, so that with a turbojet, you have to have momentum as mass times velocity. You can't have as much mass, so you've got to have a higher velocity, and it causes a lot of wind shear at the end when it comes out and enters into the still air, and it's very noisy. Whereas a turbofan has a much bigger aperture, and so it can increase the mass, so therefore reduce the velocity, and you've got less wind shear, so they're much quieter than turbojets. Next question. The new Boeing 787 uses carbon fiber epoxy composite. Provide 2 advantages to society of using this. Carbon fiber is much more resistant to corrosion than aluminium alloy. So therefore, you can have a much better regulated humidity in the plane. You can have more water vapor in the air, and it's much more comfortable for passengers. Also, because of the high specific strength of carbon fiber epoxy, you can have larger windows, because windows are stress raisers and they have to be small in an aluminium alloy frame. And the carbon fiber has a much higher resistance to cyclic stress, which occurs in aircraft, than aluminium alloy. Next question is a stress strain or a load extension diagram. Bicycle frames are commonly made from aluminium alloy and mild steel. A load extension diagram for both materials is shown below. You should be able to recognize this straight away, that that shows a definite yield point. You can see it just goes down there. So this is definitely mild steel, and you can see the ductility of it compared to this one here, which hasn't got a definite yield. So therefore it's got progressive yield. And so this would be typical of aluminium. So which material is more ductile? Obviously A is, because it extends much greater. Ductility is the ability of a material to be drawn into wire without failure. It shows progressive yield. This one here shows progressive yield. This one shows a definite yield. Progressive yield has not got a definite yield. Which one is stiffest? The stiffness is Young's modulus, and it's the angle of the straight line section. So this one here has got a lower angle to the vertical than that one. So therefore, this one A is the stiffest. Which one is the toughest? The toughness is indicated by the area under the graph, and obviously A is the toughest. And which one's mild steel? This has got to be mild steel because it's got a definite yield point, and the other one obviously is aluminium alloy. Next question, calculate the Young's modulus for material A, given that the specimen has a gauge length of 50 millimeters and a cross-sectional area of 100. Now, this question has actually given you the extension for a particular load there. So Young's modulus is equal to PL over delta L times A, which is the Pli formula transposed. And so you've got the 24 times 10 cubed. So that's the load up there, 24 kilonewtons, 24 times 10 cubed, times 0.05. And the gauge length is 50 millimeters, which is 0.05 meters, divided by delta L, right? So the you can look up here and you see what delta L is. This is how far it extended because we're using this. So it's 0.06 there, times 10 to the minus 3. You've got to make sure that you convert it to meters. Multiplied by 100 times 10 to the minus 6, because the cross-sectional area is 100, and you've got to multiply it by 10 to the minus 6. And you get 200 gigapascals, which is quite common for mild steel. Precipitation hardening is on page 54. Make sure you know that there are 3 steps, and you can get that from the marks here. So there's 3 steps in precipitation hardening. You heat the alloy to a temperature so that a uniform structure is achieved. So you've got one phase at that temperature. You cool it, and you cool it according to what the material is. The heat treater will know whether it's cooled quickly or slowly, and they cool it at a rate so that it retain the uniform structure at room temperature. And at room temperature, it's in a state of metastable equilibrium. The atoms don't want to be where they are, and so you can either let it age harden so that the finely dispersed precipitate becomes more mobile and they gather in zones in a certain amount of time, or you can heat it lightly and it will put more energy into the system, and the precipitate will form into these zones. Now, when they form the zones, they're straining the bonds, and it's making the material harder, stronger, and less ductile. And that's what precipitation hardening is. D, mild steel tube for bicycle frames can either be cold drawn or hot rolled. Now, when you show cold drawn, you've got to make sure that you show elongated grains. And that's called grain flow or grain fabric. And it's like timber, it's stronger in the direction of the grain flow. And hot rolled, you've got to show equiax grains, and these are non-metallic substances, that they're inclusions that have come from the mold, and these are still aligned in the direction of previous rolling. So that when hot rolling occurs, they allow it to cool slowly, and so you've got equiax grains. But while the rolling process takes place, these non-metallic inclusions are aligned. And that's why hot rolling is stronger than just common casting. Next question. I've missed one, have I? Oh no. Question 24A. Okay, a hydraulic system has an efficiency of 80% and a mechanical advantage of 6. The diameter of the input is 540. Calculate the distance the output or load cylinder moves when the input moves 50 millimeters. So um, So the mechanical advantage, as you know, is efficiency times velocity ratio. So therefore, velocity ratio equals a mechanical advantage over the efficiency. Now, the mechanical advantage is 6 divided by 0.8, and that will give you the velocity ratio, which is 7.5. Velocity ratio is the distance the effort moves over the distance the load moves. So therefore, which equals 7.5, the velocity ratio up here. So the distance the effort moves is 50 over 7.5, which is 6.67 millimeters. And that's the answer to that in millimeters. So the distance of the output or load cylinders moves 6.67 and the input only moves 50 millimeters. Okay, explain two mechanisms of how fibers in composite materials prevent crack propagation. Well, fibers act as crack stoppers because as the crack propagates through the material, it hits the high tensile fiber and it opens up the radius ratio of the crack. So it increases the area of the crack. And to increase the area of the crack, for the crack to go any further, it needs to have enough energy to overcome the energy required to create new surfaces. So that's basically how fibers stop cracks from moving through. Also, it hits a high tensile fiber, and the fiber will deflect the crack and stop the crack from moving. And that's basically why people, if you get a crack in the gullet of a saw or in the windscreen of a car, they drill a hole at the end of it to increase the surface area, and it will stop the crack from propagating because it needs more energy to create more surfaces. And once you increase the surface area, it generally stops the crack. Question 24C. This is a nut and a screw from a bolt. Identify the type of corrosion present and explain how it has occurred. I've given the answer, there's galvanic corrosion, and that's what most people would say. But I also accepted differential aeration. You can get corrosion occurring where there's a deficiency of oxygen. It's just like waterline corrosion. You get corrosion just below the surface of the water because there's more oxygen just above compared to below. And so that's basically the answer to this question. So galvanic corrosion occurs where you've got two dissimilar metals in contact, and the metal that's more reactive than the other will form the anode, and that will give up electrons, and that will start to corrode. And the same thing with differential aeration, where there's a minimum of oxygen compared to the outer surfaces, you'll get the anode forming where there's a minimum of oxygen. So both answers are correct for that. Next question is a question that gives students a great deal of anguish. And if you do these using graphics, it's much easier. So here you've got a block, it's on the verge of moving up. So you know that the force of friction has got to be going down. Always opposes motion or the tendency for motion. So the first thing you do is to put all the forces on. So you put your normal force here tell the examiner that that's always at 90 degrees. You project that force down there because we're going to try and get this as a three-force rule question. Then, using your set squares, you just draw that, put that force down here, parallel to it, and that will be P. And then you put your force of friction in. So the force of friction will oppose motion. Whoops, something's gone wrong. So you've got your force down there. I don't know what that is there. So, and then you complete your parallelogram and you get the resultant of those two forces. This will be the resultant. That there will be theta, which will be the angle of repose. And so over here, we have got tan phi s equals mu, and mu is 0.5. So phi s is 26.6. And so we've got that angle there is 26.6. You draw that in with your protractor accurately. And so you've got 1, 2, 3 forces acting on this body. And so we can use Bose notation. You do your scale here. Make sure you make your scale the largest force, make it equal to between 30 and 100 millimeters, and you'll get a significantly big force diagram to make it accurate. So you start with the known force. I always use Bose notation. So here we have A there, then we've got B, and then around here we've got C, which C there. And so you start with the known force, so you draw that 100 millimeters long or 50, what I've got here, and then you call that force AB, so little a, little b. Going clockwise, the next force is BC. It goes through B and it just projects up there. And the next force is CA and it's got to go through A. So you just transfer that angle up here. And so you've got your force diagram. So straight away, you can work out, you just scale off this here, that distance, and you've got what P is. And you can see that it's fairly accurate. Here we've got, using graphics, it's 830 newtons. Here's 836. So, and I've used the sine rule for that. I think the sine rule is much more difficult because you've got to work out what these angles are here. But if you want to use the sine rule, that's fine to use the sine rule. Okay, next question. A car has a mass of 1.5 tons, allowed to coast down a hill of altitude 60 meters. The loss of energy due to frictional resistance when the car reaches the bottom of the hill is 500 joules. Calculate the velocity of the car at the bottom of the hill. So you make your statement, potential energy at the top equals kinetic energy at the bottom, plus the energy absorbed by the friction. And so you just mgh equals half mv squared plus 500. You've got v squared equals that. And so you get 34.6 meters per second. They ask you for kilometers per hour here. And so you convert it to multiply it by 3.6 and you'll get kilometers per hour. Next question, plywood is a laminated composite material used extensively in engineering construction. Explain why plywood has a higher specific strength than unmodified timber. And you can see you've got two marks here. So generally you want two responses. So the first response would be that the grain is put for the veneers, is put at 90 degrees to one another. And that's why you've always got odd numbers of ply. So the grain on the outside of plywood always goes in the same direction. So you don't have 2-ply or 4-ply, you have 3-ply, 5-ply, 7-ply. So that's the first reason. With the grains going at 90 degrees to one another, it makes the plywood more isotropic in strength. In other words, more equal strength throughout. And the second thing that they do is they glue the veneers together with resorcinol formaldehyde if it's a marine ply, or urea formaldehyde if it's a construction ply. And so that interface between the veneers adds a lot of strength to the plywood. Next question is a question on triangulation. You've got to create the true shape of the plywood sheet, beginning with side AD as the starting reference. So this is how you do it. You make sure that you know the rules of true length. You ask yourself, is AB a true length? You look in the other view. If it's not a point, nor is it horizontal, it's not a true length. So that is not a true length. You say, is this a true length then? You look up here, you see it's not horizontal, it's not a point, so therefore that's not a true length. Now you see DC. Is DC a true length? You look down here, it's horizontal, so therefore that's a true length. Is this DC a true length? You look up here, it's horizontal, so therefore it's a true length. BC down here, is that a true length? It's not a point, nor is it horizontal, so therefore that's not a true length. Now the idea to get a true length is that if you know how high one point is above the other, and that's a true length, right? If you can see that how high it is above the point below, you can use that as a true length, and then you use your base length when you put your compass on here. So when I put my compass on AB, I'm getting the base length of the triangle. And so I can put the base length down here, and then that's a true length. And so this is a true length. And so the hypotenuse will be a true length. And so if you want to put get the true length of AD, put your compass on there, and then you mark it down here. Now that's how high A is above D, and that will give you the true length of AD. So let's do it. So you've got to start with A there. Now I want to get the true length of AD, so I put my compass on there, and that's the base length of the triangle. And then you mark it down here, and you see how high A is above D, and then so that there will be the true length, and that will give you that true length of AD. Now, by triangulation, we've got to get AB. So we put our compass on here, we get the base length of AB. Now that's how high A is above B. So you go out here, you mark it, I've marked it there, and so that'll be the true length of AB. So you put your compass on there, and then you mark an arc. Now to get B, you go from D to B. So D to B, you get that as the true length of the base. You see how high D is above, there's how high B is above D. So you mark it down here, and then you go up to B, and that will give you the true length of DB, and then you mark it there, and that's how you get point B. And you do exactly the same with point C. And that's called triangulation. Next question. bending moments. So here you're given a beam and you're asked to find the shear force moment, a shear force diagram and the bending moment diagram. So the first thing you do is to work out the reactions, and you can just visually look at these. It's symmetrical, and so you've got a total of 10. So you've got a reaction of 5 up there, and you've got a reaction of 5 up there. And so you follow the force rule. You it tells you to go up 5 because we don't do UDLs. You go horizontal, and then it tells you to go down 5. So we've gone down 5. Then you go along horizontal, of course, no UDLs. Then it goes down 5, and then you've got the reaction up 5. So if you end right at that point, you know you're correct. Then to find the bending moment, maximum bending moment, all you've got to do is take a point here and you multiply that distance by that force. That force going up there is 5, which is a reaction here. So 5 times 0.5, because that's 500 millimeters, that's 2.5 kilonewton meters. And so you just go up here 2.5, horizontal, because there's no DL, and then same bending moment there, and down 5 there. And that is your bending moment diagram. Now the next question says, determine the maximum bending stress in the C-beam, assuming the second moment of area of the beam is 40 times 10 to the 6 millimeters to the fourth. So you have a look here, you see the maximum bending moment is 2.5 kilonewtons. And so bending moment is equal to 5 times by 5 is 2.5 kilonewton meters, because it's a moment. And sigma equals my on I, which is given in your formula sheet. And so the bending moment is 2.5 times 10 cubed, because it's kilo, multiplied by 0.1. Now this 0.1 is the outermost fibre stress from the neutral axis. So this is a symmetrical beam, and so therefore the axis of symmetry goes through the centre, and the largest distance of the outermost fibre is the same on both sides, so it's 100. So you've got to multiply that by 0.1, bring it to meters, divided by the second moment of area. Now, they've given you the second moment of area as millimeters to the fourth, and we've got to convert that to meters to the fourth. So you've got to multiply that by 10 to the minus 12, and that comes out to 40 times 10 to the minus 6, which is 6.25 megapascals. And that's the answer to that. Next question, how does the concept of lift relate to an aircraft wing and Bernoulli's principle? Well, Bernoulli's principle says that if you accelerate air, you've got to decrease the pressure to make the energy before equal to the energy after. So a wing is designed to accelerate the air over the top of it. And so when you accelerate it, you have to reduce the pressure energy there. So it produces a low pressure area compared to the pressure underneath the wing. And that's what causes the lift, according to Bernoulli. And some people put the Newtonian effect with the wing at an angle and it's forcing air down, and to every action there's an equal opposite reaction, and that's what forced the or added to the lift. But the question asks you about Bernoulli, so you have to answer according to Bernoulli. Next question, why are most optical fibers used in telecommunications single mode fibers? Look, single mode fibers are used because they require less boosting and they allow for only one light path to travel through. And this reduces attenuation of the energy and dispersion, and you're allowed to, or allows you to have longer transmission distances with less data loss. Multi-mode fibers, they suffer from a lot of dispersion, which you don't have a good quality of signal over long distances. Next question is a orthogonal question. You've been given a pictorial drawing and you had to do a half section of this pictorial drawing, and you've had to do a left side view and a sectional front view. And so make sure that when you do this, if you've got two different materials, which you have here, you've got bronze bearing and cast steel, you've got to show different hatching angles. It doesn't matter what angle it is, but you've got to show different hatching angles. When you're showing a section, you've got to put on the view that you're sectioning these section arrows so that you're looking in that direction, and the chain line ends in thick dark lines to show the end of the section. Next question, describe the nature and range of work of aeronautical engineers. The nature of work is what the aeronautical engineers are engaged in. It's like designing, developing, testing, and working out aerodynamics, propulsion systems, and using structural analysis to work out the structure of the frame. And the range of work means what various areas they can work in, and they can work in commercial, military, helicopters, drones, satellites, etc. So that's the range of work. Explain why the factor of safety is higher in civil structures like bridges compared to aircraft. Well, the fact that bridges don't have to be subject to rigorous testing like every component in an aircraft means that the engineers have more confidence in the materials and the components that go into an aircraft because, for example, they'd never use sand casting and every material is tested for crack testing and structural integrity. And so there's more confidence in an aircraft to for the materials so that you can reduce the factor of safety. And the other reason is that the lighter the plane, the more payload and the more money that the plane can earn. So it's imperative that airlines have a low factor of safety to keep costs low and safety high. And the reason why safety is so high in aircraft is because it's very rare to have failures because of the rigorous testing of the components. So the factor of safety of a bridge could be 2.5, but the factor of safety of an aircraft could be only 1.4 or 1.5. And that's the end of the paper.